Hi guys and welcome. Can you believe it? It's that time of the day, Learn Extra Live, and Tracy is with us. Today we're doing physical science, just in case you didn't know. Guys, we have an amazing lesson planned out for you, and you know what? Happy Valentine's Day, everyone.
Yes, happy Valentine's Day.
Hey, here's a little heart for all of you guys. So Tracy, tell us, what are we talking about today?
Today we're going to do atomic structure. We're going to do a little bit of how the atom is structured, and then we're going to look at trends on the periodic table and how the periodic table is structured for a little bit.
Perfect. Yeah. And I know that all of you mindsetters out there have been asking about the periodic table. Guys, now is the time to get those questions in. We want questions that are related to what we're talking about, because we've got a plan, we need to stick to it. So get chatting to us on facebook.com/learnextra, and that's with an XTRA. Also on Twitter, follow us at LearnExtra. Get chatting to us, get those questions in, and we'll see you after the break. Hi guys, and welcome back. We are excited for a fantastic, amazing show. Guys, get chatting to us on Facebook and on Twitter. I've just opened up and I'm super excited to be speaking to the grade 10s. Also, I know grade 11s and grade 12s, I know you're also tuning in, so you can scratch up on those skills. That's okay too. So chatting to me, and I think I'm going to go straight away to Tracy. Take it away.
Thanks, Indiana. Well, what we're going to do is we're going to start right back. Last week we were talking about history of the atom and all the rest, and we got very excited, realized I don't know everything, which is quite sad, but it's okay. And we got to where we were speaking about Bohr's model, and we spoke about the different energy levels. And his model is what we use for the structure. Now, the way we can draw it, and I'm going to just quickly draw it on here for us, is we represent the nucleus as a little dot. It's not at all to scale. There's no way we can make it to scale because it's so tiny. And then we put our energy levels. I'm going to have to just make, at the moment it's a black circle, so I just want to quickly change it to a white one, otherwise you're not going to see it. And that would just be terrible, because you need to be able to see the circle. Okay, so when we often will draw a circle around it, and what that does is this circle represents our, if it wants to move for me, it doesn't want to move. Let's try that again. Anyway, just pretend the circle's in the middle here today. It definitely doesn't want to move. Nucleus in the middle, we draw a circle to represent the first energy level where we will put electrons. So if we're looking at hydrogen, for example, hydrogen we know is the first element on the periodic table, has 1 electron. So what we can do is we draw a little dot on there, and that represents my hydrogen. Okay, now what we have there is a very bad sketch, but it's close enough for you to see that we have the nucleus in the middle and we have 1 electron around the hydrogen atom. If we now move on to the next element on our periodic table, which is helium, helium has 2 electrons in its structure, and what they found is that the helium electron we would represent by drawing it there. Now, this has become a helium atom. Inside, we would have added another proton, okay? And this structure is very stable. Your helium, I'm hoping you'll all remember, is in the very last group on your periodic table, which we traditionally call group 8, known as the noble gases. And that group, very stable. Helium loves this structure. But then we go on to the next element, and that's lithium, okay? Now, lithium has 3 electrons. And what scientists realized is I can't just draw another electron here because there's no more space. Remember from electrostatics, your electrons are negatively charged. Those negatively charged electrons they don't want to share space with each other. It's like you and your siblings, let's be honest, when you're younger, you don't like sharing your toys, you don't like sharing your space, and electrons are the same. So the maximum they are going to allow in one little ring like this, at this point, is 2, okay? But then scientists realized we go to the next level, and it doesn't want to draw. Come now. There we go. Let's try again. This board really doesn't like me.
No, you're doing so well. Look, you're even making fancy shapes. Try again.
That's because it's black. That's why. It's black.
There you go.
There we go. Okay, so now we have our next energy level, okay? Into this energy level, okay, we can now put some more electrons. And if we go to lithium, we have 3. So now we have 3, okay? But the next element on our periodic table, if I am correct at this point, is magnesium. But I'm just going to have to quickly check that. Sorry. And it's gone away. Look at that. Is beryllium. I lied to you. And beryllium has 4 electrons in it. So we can put another electron there. So the point is here, we can just keep increasing the number of electrons we add into the structure. But this doesn't help us very much, because in reality, these rings represent what we call orbitals, okay? And these orbitals are very specific. Only 2 of them can share a space. It's like when you go on a school trip and you sit in the bus. And if you have a choice, you will want to sit on your own, but most school buses only have enough for 2 people to sit next to each other, okay? Because that's just the way they are. So they only like to have 2 in the same space. So what is that? How does that help us? Because if we now move on and we get to oxygen, okay, oxygen's a good one. Oxygen has 8 electrons, okay, in total. So if this is starting to be my oxygen, I've got 4 so far. So I would have to do 5, 6, and then 7, and I'd put 8 there. And there's a random one just in the middle. No, it's fine. It hasn't. There we go. Okay, that's 8. Did you notice what I did? At least I hope you did. That what I've done here is I put them in pairs here. I didn't put them randomly because it's not random. It sounds fairly random, but it's not. These actually have shapes. Now, the very first orbital we have, and I am going to do these freehand, and it's going to get a little messy, but I'm hoping you'll actually just stay with me on this one. I'm going to put that there, okay? Is the first orbital shape we have is an s orbital because it looks like a sphere, okay? So it's I'll do it from this side, it's a circle. Okay, so that's the little one, holds 2 electrons. Then, on top of this, we get another S, which sits here. It's got a little bit more energy, okay, but it sits on top. The further out we go, and this is very important for trends, the further out we go, the less the electrons are attracted to the protons in the nucleus, okay? So the properties start to change. But this S orbital isn't the end of the second energy level. It's actually just the beginning, because on top of this, we get p orbitals. And p orbitals look like dumbbells. That's how we describe them. And they are 3 sets of orbitals that go at right angles to each other, which is a little bit hard when you're dyslexic, and a little challenged sometimes. But they're at right angles to each other in 3 dimensions, okay? But they're like figure 8s. So they go and fit over like this. And they do that, and then you have another one that goes there. Okay, so now it starts to get lots of fun, and I'm hoping that in this squiggly line on the board, you start to see that nice diagram of the atom we often get on TV when they're trying to talk about how electrons move around, and it often looks like this, okay? But this in total only takes 10 electrons, so we now get to the next energy level, and it starts with an s orbital that sits on top of these 3 p orbitals, and then it also has 3 p orbitals that now do that. And it's starting to look a little bit more like a proper diagram. Okay, but it just gets messier and messier and messier. And I'm hoping some of you at home are going, hang on, wait, they seem to overlap each other in the middle. Yes, they do. But remember, your electrons won't stay there. Then they might, and it's very random. In fact, scientists have realized that you can do one of 2 things with an electron. You can either predict where it's going to be, or you can tell me how fast it's going, but you can't do both at the same time. So these electrons move extremely quickly, all over the place. And if they come too close to the nucleus and they're the outer energy, they will move away. Okay? Now, this diagram doesn't really help us, let's be honest, because that's a bit of a squiggly mess. And I know if my kids drew this for me, I would have a bit of a moment. So we have a way of dealing with it, and this is what we call the Fby diagram. Okay, now Fby is the German word that means building up, and this is a set way of writing the electronic structure so we can represent this. So we can represent this. Now, we're going to leave you hanging right there, because I'm hoping some of you have done it, and we're going to take a quick break, and then when we come back, I'm going to put squiggly lines into nice little neat blocks. Okay, so we'll see you in a second.
Hi guys, welcome back Mindsetters. I hope you're enjoying the lesson so far, because we are. I mean, I'm learning a lot, and I do every single show. I think I even surprise Tracy from time to time. Okay guys, we have a question on the page that I think is quite important that we should get to right now, and Tracy has said yes, she will go through it for us. Now this one is from hold on, let me see if I Cholanang. I'm going to go and I'm going to practice your name, and by the end of the show I'm going to be able to say it fluently, I promise you. And his question is, actually I think it's a her, she's wearing very pretty glasses. Okay. I like them. Can you please explain valency? Please. And I'm sure a lot of you are saying yes.
That is such a good question. I'm so glad it came up now, actually. Valency is something you guys have probably heard, and you've heard about valency and you've heard about valence electrons, okay? They're similar, but not quite, okay? Now, if we go back to my squiggle of oxygen, okay, now here, oxygen has 8 electrons in total. The electrons that sit in the very middle, okay, and I've moved something around, okay, I've moved the electron around, look at that. Okay, the electrons that sit in the middle, those are known as the core electrons. They're not important when it comes to your bonding. The 6 electrons that sit on the outside of my oxygen atom, in this case, they are important. They are known as valence electrons. Okay, now these valence electrons are the ones that take part in bonding, and they determine how quickly an element's going to bond, how fast, what sort of bond it's going to make, whether it's going to be covalent, ionic, which we're going to get to eventually. But the 2 that I haven't ringed, so these 2 electrons over here, this one and this one, those are the electrons that really are very important. And we say oxygen has a valency of 2. Okay, now some of your books are going to say that oxygen has a valency of -2. That's just to teach you that oxygen is actually going to take 2 electrons from whatever it's bonding to in order to get this outer shell to have 8. Okay, but it has a valency of 2 because it's going to make 2 bonds. All right, if we go to chlorine, chlorine's in group 7. Chlorine has 7 valence electrons, 7 electrons in its outer shell, but it only has a valency of 1 because it only has the ability to take 1 more electron to complete its outer shell, which then gives it this nice noble gas structure, which is what we want. So its valency is 1. Sometimes your books will say it's -1. That just tells you it's going to take electrons rather than give. Okay, and so we know what its valency is. If we look at our group 1 metals like lithium, sodium, potassium, they also have a valency of 1. So chlorine has a valency of 1, lithium has a valency of 1, but lithium is sometimes described as having a valency of +1 because lithium will give its electron away. It's a metal. Metals don't really like the electrons. They give them away quite easily. So it has +1. The nice thing about your lithium and beryllium, which is in group 2, and aluminium in group 3, is their valency is equal to their group number. Okay, so, and their valency and their valence electrons are the same. Group 4, where we get to carbon and those sort of elements, they have their own little moment as to whether they're going to give electrons away or take electrons, how they bond with them. In fact, carbon has a branch of chemistry known as organic chemistry all to itself. because it can bond so nicely by itself. Then we get to group 5, 6, and 7, our last 3, and there your valency is not equal to your valence electrons. But because the way we remember it is it goes 1, 2, 3 in the group numbers, then there's 4, and then it goes 3, 2, 1. Why do all our elements bond? They want to look like a noble gas. That's what they want. The noble gases are your superstars on the periodic table. They're the ones with all the money, if you want to think about it that way. They're like your favorite singer or your, the person who lives on the hill. We all want to look like that because then they think they're stable and they're very, very happy.
Do you know, I actually got that question from Mbuso on Twitter. So there you go, Mbuso. I was just about to type back, I'll ask Tracy, but I don't even have to. Tracy has answered.
The question was why do they bond?
What are noble gases?
Oh, noble gases. They're a strange little group of elements.
They sound fantastic.
They are. They're called noble because they're very stable. They're also known as the inert gases. So we don't just call them noble gases. A better word probably is inert. Inert means that they don't react. So you can't find helium bonded with something or neon or krypton and no, that's not the thing from Superman's planet. It is actually an element on the periodic table, but it's just the nice ones. They've got their full electron structure. They're very happy. They are at a very low energy state. Okay, so they are stable. They're quite happy to be who they are, and everyone wants to be a noble gas. So I hope that helps, and I'm hoping we've cleared up the valency.
I did. I've got a few more questions.
Sure.
Guys, thank you so much for sending in your questions. You'll see now when you send in questions that are relating to the topic, how fast and how much work we can actually go through. Okay.
Excellent.
Let me have a look. Okay, this one's from Sontaga, and it's relating to this question. Do electrons in the same orbit have the same speed and energy level?
They do have. Speed's a difficult one because they can't accurately predict their speed and their position, but they are considered to have the same amount of energy. That's why they sit in that energy level, okay? But remember, when we were talking about the S&P, in each orbital, they have the same energy level. So in this first energy level, they have the same amount of energy. When we get to the second energy level, it's broken into our 2 parts, which is your S orbital and then your 3 P orbitals. The P orbitals are slightly more, but you've also got to remember that your electrons have to travel a further distance. So if they have to travel further, they're going to have to move faster. Okay, so the further away we go, the more energy they have, the further away we go. Yeah.
Amazing. Thanks, Tracy. Okay, here's another one.
Yes.
This one's from Kehotatso, and I think he wants to know, why are they in pairs and not single?
Okay, this is also, it's actually a very interesting question.
Good one.
It has to do with the stability, okay? So remember, the whole point is we want to get to a lower energy level. And if our electrons are just all in singles all over the place, then it becomes a real issue. But it's a good question because I think the question's coming from, but we know that if we have 2 negatively charged objects next to each other, they're going to repel. So how is it that these electrons are now sharing their space? Well, the electrons I've just said aren't actually stable. They're not just sitting there. They're moving around all the time. But the electrons are like us on Earth. We travel around the sun, okay, so we know we've got a fixed orbit around the sun, but as we travel around the sun, the Earth also spins on its axis, which is why we have night and day, which is a good thing. Scientists can't explain why at this point. Electrons spin on their own little axis as well, so they move around the center of the atom and they spin on the little axis, but as they spin on their axis, they create a magnetic field, okay? Now, depending on which direction they're spinning will determine the direction of the magnetic field. And if they're spinning in opposite directions, which I can't do with my hands, okay, then the magnetic fields are opposite. So like the poles of a north and south pole that are attracted to each other, this allows them to spend the same space, to share the same space together, because they have to spin.
It's incredible. It really is incredible. Okay, we're going to have one more question. I know the producer wants to go to break, but I think it will be a very quick one. I hope so. How do you know how many electrons should be in one orbit?
It's always only 2. It's always only 2. After the break, when we take a quick break, we're going to look at Fby diagrams, and then that explains it really nicely to you. So
and that's for
only ever
treasure.
2.
So treasure, It's only ever 2, Treasure. Yeah, don't forget that, Treasure. So, guys, Treasure, all of you guys that are sitting and watching, we're going to go to a short break. Please get those questions in. We're talking about the periodic table. What else? What other questions can they send in?
Electron structure.
Yes.
It's pretty much where we're going.
Send them in and we'll see you right after the break. Welcome back, guys. I see that we are now live. Guys, happy Valentine's Day. If you want to send through a few love messages to our wall, that's fine too. Tracy, let's get straight to it. And guys, don't forget also questions. Send us through questions. Questions of love as well.
Well,
okay.
Don't know if I can explain those ones, but we'll try. Anyway, so we've been looking at electronic structure. So we know I'm going to look if we have helium. Remember, helium can have, me hate this board.
No, you don't. You love it.
I do love this board. Okay, so the helium gets 1 electron. So that's hydrogen, number 1 on the periodic table. Helium, we can now put 2 electrons, and that's the first energy level that's complete. Then we get to the second energy level. Okay, and as we go across the periodic table, that means I'm going into the next group. Okay, into the next period, 1 level down. And the next one on our periodic table is lithium, which has 1 electron next. It has 3 electrons in its structure, and it has 3 protons. The next element on the periodic table is beryllium, which has got 4. So now we're doing quite well. And instead of just going into drawing another circle, making another energy level, scientists realized that actually we can just add more electrons into here because there's still space for these electrons to share. Okay, and in fact, if we go to oxygen, which is group 6, it has 8 electrons. So we've done 4 already, and we can do 5 and 6, and then we go, oh, hang on, wait, now we've got 4, now I've got still 2 missing, and what scientists realized is that they're going to now spend time together in pairs, okay? And these pairs, each of these pairs, so if we look at that one and that one, they're actually orbitals that form part of an energy level. Okay, so if this is the oxygen, so this is our oxygen atom, that oxygen has 2 energy levels, and it actually contains, the first energy level is an orbital, has 1 energy orbital, 2, 3, 4, has 5. Okay, and your orbital, and I've put the definition there for you, is the region where an electron may be found at any one time. Your electron configuration is our arrangement of those electrons, because that is really important. If we go on to calcium, which is the 20th element on your periodic table, what that means is, obviously there's lots of electrons now. So if we fill in calcium's electron structure, it's going to be 1 and 2. That's the first one finished. We've realized that. Then it's going to do 5, 6, 7, and 8, and then 9, 10, 11, 12, and we're going, oh my word, well, that's not 12, that's actually 8. I can't count either, so it's a good counting exercise for you. That means this energy level can also get 8. Okay, but I'm hoping some of you, your maths and your arithmetic is better than mine, and you're going, hang on, wait, Tracy. 8 plus 8 is 16, plus 2 is 18, and you just said to us calcium has 20. Yes, it does. Calcium is the biggest electron structure that you are going to have to draw, which actually means for calcium, I need to put in another energy level, okay, which is a 4th energy level, goes into the 4th period, and that one takes 2 electrons, okay? That's as far as we go. After this, after 20, we spoke about the s and the p orbitals. After 20, we have to start introducing orbitals known as the d and the f. And that just starts to get really complicated. So we don't need to worry about those. You only need to know about the S and the P, okay? And this is the biggest one you're going to get. But let's be honest. If your drawing's as good as mine, then this just becomes difficult to do things with. So we're going to look at the Fby diagram. Now, an Fby diagram is actually such a useful tool for us because instead of representing our energy levels as circles, okay, we represent them as blocks. And we've actually broken it up into a set of blocks where we have 1s, 2s, 2p. Okay, so we have our blocks, and we're just going to make them so that you can actually see them, because of, let's do, there we go. Okay, so, well, that's not what I wanted either. Yeah, that's the one I wanted. Okay, so we're going to make it so you can see it, because otherwise it sort of defeats the object. There we go. So there's my first one, it's my 1s, okay. Now the 1s represents that first energy level. So what do I put into that 1s? How do I represent the electrons? And this is quite important. And here, if your teachers teach you to do a full arrow, please don't worry about it. It really isn't a huge thing. But to be technically correct, when we represent the electrons, we represent them. So if I'm drawing hydrogen, I would draw one electron. Oh, man.
Oh, it's in black again. That's why, Tracy.
I don't know why. It doesn't.
Bamboozling you.
There we go. There we go. Okay. And let's just move the Fby diagram up. No, tell you what. Should we just draw our own? How does that sound?
Yeah, let's do it. I think you draw it lovely.
There we go. Let's start again. So, and it's black.
It's testing your patience. I think you're a very patient lady.
I don't think it's just my patience it's testing right now. Okay, so I'm so glad you guys are being patient with us. This on your page would be a normal block, okay? So we're just gonna, and we call this the 1s, and we draw a half arrow on it because the half arrow represents the spin. Because remember I said to you that in order for the electrons to share space together, they've got to spin in opposite directions. So this would be hydrogen. No. This would be hydrogen. Move on to helium. Helium has 2 electrons. So helium, in order for the 2 electrons to share space, helium's electron must point down. So now we've got 2 electrons in my first orbital. That wasn't so bad, but what about when we go into lithium and now we have our second energy level, and here's where life gets very interesting for us. So what we're going to do is we're going to quickly add some more of these, okay? And there's my block, there's my s orbital. I'm going to add some more. And now we're adding in, what we're doing is we're busy creating my second energy level, which I drew as a circle. That energy level, okay, which you draw nice and neat, is now my second energy level. That is 2s, which we label as 2s. That is labeled as 2p, okay? So where does that take us in terms of where we're going? Well, if we look at oxygen, let's skip to oxygen, which we know has got 8. So we don't need, it's not helium anymore. We're now looking at oxygen. Oxygen has 8 electrons. It's number 8 on the periodic table. So we've already got 2. So that's, let's make it so you can see it. That's number 3. That's number 4. Now, how do we go about filling in the rest? Because this is how I knew what to put in pairs in the last diagram. So we've got 4. Now we go 5, 6, 7, 8. Okay? So we fill up each orbital separately. Okay? The 1s, the s orbitals get filled up first, lower energy. Okay, and then we fill up the rest. It's like when you get on a bus, okay? And if you're like me, I don't always like sitting next to strangers because I'm actually quite shy. So if I have a choice when I sit on a bus, I'm going to sit on a seat by myself because then I don't have to make small talk. Same thing with the electrons, okay? They don't want to share their space. So if they can, they're going to have their own orbital. This is a wonderful model for us because when we look at bonding and we spoke about the noble gases, the point is we want this energy level to be full or to be completely empty, either way. So it's easy for us to remember looking at this. Oh, wait, hang on. Oxygen has space for 2 more electrons. That is its valency, but it has 6 valence electrons because it has 6 electrons it can possibly throw away. But let's be honest, it's easier to take 2 than to give 6. Okay? And in fact, if we now change this into fluorine, which is at the top of the periodic table, if I'm not mistaken, okay, fluorine, ooh, maybe I should learn to write too, looks like that. Okay? 1 space. It desperately wants another electron. Okay? Desperately, desperately, desperately. It will not give it 7 away. Same with chlorine. Not going to happen. Or bromine, because it's easier to take 1. This takes us to our next energy level. So when we now go, because remember we're not going to go further than 4, okay, and I'm just going to select a whole bunch, I hope, or not. I'm going to try. There we go. Don't know why it keeps doing that. Don't move me. There we go. Now we're going into our next energy level, which looks exactly like our third one.
Can I ask you a question?
Yes, please do.
What is the name of group 1 and 2? Faith says that her books don't have the name of the group.
Okay, that's actually a very good question because you actually do need to know these. If I can move this, we'll move it just now. Group 1 is your alkali earth metals, and group 2 is your alkali metals.
Fantastic. So
Okay.
Faith, I hope you heard
Yes,
that.
and the alkali metals, because when they react and they bond with oxygen, for example, they form a base. And a base dissolved in water is an alkali. So it makes it nice and easy. Okay,
Perfect. See, a nice short question. I like that.
I like those as well. Yeah, because it gives me a chance to try and move this, but we're not doing so well with the pen thing. There we go. Let's take that away. There we go. Okay, third energy level. This now starts, and we call it 3s and 3p, and we will just fill it up as we go along, just like we did with the last one. So the next one, if we go on to our third period, group 1, the next one that we're going to look at there is going to be sodium. Okay, sodium has 11 electrons. Okay, and if you're saying to me, how do I know that? I've been teaching for a long time. You start to know these things in your head. So we've already got 10. The next one goes here. Okay? And that's sodium. Now, what would be a very, very, very good idea for you to do, and it's a little bit of a homework exercise for you, is draw 20 of these diagrams, okay, including, I'm going to show you now, the 4s orbital, okay, because that's as far as you have to go. So I want you to include the 4s orbital, and then I want you to fill them in as you go along your periodic table. Okay, so in other words, you start with hydrogen just like we did, and you fill in for hydrogen, helium, and you go along, okay, because this is going to get us to trends. Then you cut all your little diagrams out, and you put it together, and you put all the group 1 elements underneath each other, all the group 2 ones, or the next one, 3, 4. You're missing out the transition metals. We leave those out because they start going into D and F and it starts to get difficult. And you're going to see a very, very important trend. Okay, remember we spoke about valence electrons and valency. Group 1 elements have only 1 electron in an s orbital, valency of 1. Group 2 elements, so the one next to sodium is magnesium, and magnesium, that's its electronic structure. Magnesium has 2 electrons in its outer shell. Okay, 2 valence electrons and 2 valence electrons. Its valency is 2. Okay, I just got to check if the next one's aluminium. I don't think it is, because I don't remember all of them off by heart, which is
very
a
fancy.
bit sad, I know.
No, it's okay.
I
Can I
tried.
ask you a question while
Course
you
you may.
check? Okay. What name is given to electrons with the highest potential energy?
There isn't a special name for them.
Okay.
No, there isn't. It's just all part of it.
So Shepherd, there is no special name.
Yeah, you know, if you're going to try and name, probably your valence electrons have your highest electronegative energy, but we don't name it. We lost the box along the way, but we're going to pretend it's still there.
You're just going to have to redraw it. You probably flicked it out into
Yeah,
the top of the
that's
screen.
okay. So after magnesium, it's actually aluminium, which then looks like, oh, it's gone to black again. I love this board.
How's about you figure out the board? I'll have a bit of a quick chat to the mind setters and speak to them. Guys, thank you so much for chatting to us on the Facebook page. You guys are sending through some incredible questions. Treasure, Lloyd, we will get your questions. Just give us some time. Guys, don't forget to, for you guys that aren't chatting to us yet, come to www.facebook.com/learnextra, and that's with an XTRA. Also chat to me on Twitter. My name's Indiana, and I'm behind the computer, and that's @LearnExtra, and that's the handle. Guys, what we're trying to do with our Facebook page is we're trying to create a little online community. And what that means is if there's anything that's on the page that you've put a question and you see, I know that, and you put the answer down, feel free to help out. We do have teachers that are going through the page and checking that all the questions are right. But this page, it's not only for us, it's also for you. And I think Tracy has now got the board to behave, so then we'll go back to her. You ready?
Extra lessons.
Hey, technology these days. That's what my parents always say.
Yeah, no, something like that. It does make me feel old. Anyway, so this is aluminium, Al, okay? The next one on my periodic table is silicon. Now, this is what I was saying to you. Silicon now has another electron, but there's a choice for the electron to either go in this p orbital or in that p orbital. Which one? It's going to go into the one where it doesn't have to share space. So silicon will put its electron there. Then the next one on my periodic table is phosphorus. So phosphorus will put its electron there. Now, phosphorus sits in group 5, okay? Phosphorus has 5 valence electrons. 5 valence electrons. But it has a valency of 3 because there's only 3 spaces. There are only 3 electrons that can take part when it bonds with things, okay? The next one is sulfur, which comes down there. Then we have chlorine, and then we have argon, which looks like that. Now we've got to our nice noble gas structure, very happy, nice and stable. They've reached the pinnacle of where they want to go, and we add another electron, and we go into group 1 again, which is where we have, this one would be potassium.
Tracy?
Yes.
I'm just going to butt in.
Please do.
You're going to hate this, but can we change the color of the pen? Because a few of the learners are saying that green's a bit funny. So I'm thinking, what should we change it to? Is there maybe a purple?
I don't know.
Yes, I'm sure.
Pink? How about
there,
pink?
that beautiful pen.
Pink?
Yeah, let's give it a bash. Let's see.
try.
Guys,
Okay.
let me know if it's easier to see.
Yeah,
Is
not
that less
so
easier
sure about
to
that
see?
one.
Okay, try the purple. Try the dark purple.
Let's take that off.
It is Valentine's Day. How about a bright pink?
Bright pink. I don't
Right.
think.
Yes, that purple down there. There. Perfect. Okay, guys, we have a pen.
Okay. There we go.
Let us know what you think of the
I'm
purple.
hoping that is better. Sure, we're doing well. See, and it's important to make it nice and colorful for you. So this is now calcium, okay? The one we did before there is potassium. I'm hoping some of you saw in grade 8 and 9 the reactions of the metals. And your potassium is the one that explodes. In fact, potassium burns underwater. The reason why it is so reactive is because of where its electrons sit. The further away we go, the more energy those electrons have, the easier it is for us to work with them, okay? And they don't want to have that much energy. They're lazy, all right? I tell my children all the time that electrons are like teenagers. They can sit and do nothing all day, they will, all right? But they don't have a choice because they've got lots of energy. It's also that whole sugar high all the time. That's what our electrons have, okay? And I'm hoping that sort of made some sense because we need to move on to trends.
Yes, definitely. But before we do,
Yes.
Arise wants to know, if you did get this kind of question on an
Yes.
exam paper, what kind of question would they ask?
They'll ask you to draw the structure. So, for example, they'll say to you, okay, we give you, let's just take this down, and they'll say to you, there's my block that went missing. They say to you, draw the Fby diagram for a chlorine atom. So you would then look on your periodic table, okay? You realize that chlorine is in this third period, okay? And what you would need to do is we would start with the s orbitals. So, and I don't know if the purple really works on the black screen. So let's change it to pink again, because the pink works nicely on
especially
the black.
for Valentine's Day. Good
There
job.
we go. All right, and this is how we would draw it. So, and I'm hoping you guys all know that you need to use rulers, very important. Now, the reason why, so I'm drawing chlorine for you, the reason why I don't draw the block exactly on top is because remember the p and the s orbital are almost the same in energy. This is my 1s, and I know that one's going to be full. This is my 2s, which I know is also going to be full. This is 2p. And so far, up to this point, I now have 10 electrons. And I've got to make a total of 17, because it's chlorine. So this really is a little bit of a counting lesson, because sometimes we can get a little lost. So that makes 12, 13, 14, 15, 16, 17. So they'll ask you to draw your Fby diagram, and then we tell them that we've drawn chlorine along the way.
Fantastic.
So I'm hoping that answers his question.
Okay, fantastic. Yeah, let's move on. And I think,
Yes.
guys, a lot of the other questions that have come through
Are similar.
and also have to do with what we're going to be talking about soon. So, guys, keep stuck to your seats. It's all coming, I promise you. Trends.
Cool. Okay, trends. Now we're going to do this really quickly. First, quick recap. Not going to spend a lot of time on this. Periods are our horizontal rows. Groups are our columns, okay? So you've got to know those terms, but it's just a nice fancy word for the groups and the columns and the rows, okay? Now, on your periodic table, oh, wrong way. The trends are very important, okay?
And then, Tracy, with
There we go.
With the periodic table,
Yes.
is it necessary to know all the 20 elements off by heart? Everyone keeps asking.
Yes. In fact, in the new CAPS document, they're saying more than the first 20.
Oh, really?
They're saying the first 20 definitely, and then your more common ones like gold, silver, tin, lead, mercury.
The ones that you should know.
The ones
Yeah.
you should know. It's a bit daunting right at the beginning, but the more you work with them, the more you're going to know.
Yeah, and the
Yes.
periodic table is quite exciting as
It
well.
is, and it's
So-
also really important because you're going to get to the point where you're having to do chemical equations far more complex than you've done, and the honest truth is we can ask you anything because we're only teaching you an application. There's not a chance your teacher or any of us can actually physically do every single type of chemical reaction that you could get or that we could ask you. So what we're trying to teach you is how to use your periodic table, how to use these tools to get to apply it and to understand another option. And also, we can describe things to you in words and expect you to write it out. So when you get there, you're going to do it reactions like with oxygen, and your teacher's very well within their rights to say, well, if magnesium burns in oxygen and we get magnesium oxide, give the chemical reaction. You need to know those reactions, but you're going to be doing this for 3 years. Trust me, it'll become
You guys will know. You
second
guys
nature.
will
Absolutely. Now, trends. Trends are going to come up, guys. Now, the only reason why I have this diagram is you do not need to know these values. Please, please, please don't learn them. This is a nice trend which we found because it shows you really nicely. It shows a representation of the size of the atom, okay? And as we go across my period, okay, towards the right, the atoms are getting smaller and smaller and smaller and smaller, the atomic radius. As we go down, they're getting bigger and bigger and bigger. Okay, now they get smaller as we go across because we add in extra negatives and positives, but we're not increasing the size of the energy level. So if we have more positive and negatives that are now attracted to each other, it's going to shrink the size. When we go down, the size increases because in every period I add an energy level. So now we add in another energy level, so it's further apart, plus these outer side electrons are shielded from the nucleus because they've got all those core electrons. So your valence electrons, which are the outside ones, are shielded from the core, so there's not as much attraction. Okay, so we learn in the trend. across it goes, decreases, down it increases, okay? And that's because of the number of electrons. The next trend is ionic radius. Radii is just simply the plural for radius. This is a strange little thing. By ionic, I'm talking about what happens when our atom loses or gains an electron. Now, your group 1 elements will tend to lose 1 electron, so they become single positive charge. Group 2 tend to lose 2. Now, these are tiny, 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 because by losing their electrons, they've actually lost an entire energy level. Okay, so they haven't just lost their friends, they've just lost the whole thing. The energy level's gone, so they shrink. When we go across to our negatives, so we look at nitrogen, oxygen, fluorine, these have all gained electrons. But now you go, okay, but now there's more electrons. Of course they are. Of course they're going to be bigger because they've gained electrons but no more protons. So the repulsion between the electrons gets a little bit bigger. All right, they don't really like the idea that they've got an extra electron friend, and they expand to make space for the electron friend to stay there, okay? Your ionization energy, you're going to see this one quite often. Ionization energy means the amount of energy needed to make it into an ion, okay, to remove an electron. Very low, except for hydrogen, it's a little bit of an exception, very low in your group 1 elements because they don't want to keep the electrons, they're happy to give it away. Very high with your non-metals, with your bottom end, okay? Because here they go, no, don't you take my electron. It would rather take an electron than give them away, okay? And in fact, to get chlorine or fluorine to look like a noble gas, has to give 7 electrons away if we're going to go that way around. It's never going to happen. The further down you go, the smaller your ionization energy becomes, because you've got less energy, you've got less attraction. So it's easier, okay? And then the last one, electron affinity, which looks very much like your ionization energy. This is going to become important when we look at electron negativity. In fact, I'd rather stop. I'm going to end off with electron negativity. This is important. In fact, the electron negativity values are given to you on your periodic table. It is the one value you are going to work with. And it ranges from 0, which isn't given in the noble gases, to 4. And it's a scale, okay? It's not a value, it's not energy as in joules or anything. It's a scale. In fact, it's the Pauling scale. Fluorine being the most electronegativity. Fluorine desperately wants an electron. It will take electrons from anything, okay? When we now get to something like francium, it's 0.7. Francium's like, oh, well, if I have to have it, I'll have it, but I'd much rather give it away. Smaller the electronegativity, also has to do with the size of the atom, okay? Big atom, small electronegativity, small atom, big electronegativity, okay? The lower the electronegativity, the more it's going to give its electrons away. The higher the electronegativity, the more it's going to take its electrons, okay?
Fantastic.
Assuming you got a question there, because it looks like it.
I do. You always know, it's this desperation. Okay, we've literally got 1 minute, and this one's from Pumi. Quickly, yes. How do we work out the ionization energy of an element?
You don't have to. It'll be given to you, and they'll just ask you to explain the trend.
Fantastic. Okay,
yeah.
And I've got another one from Axole. He is going to have a near heart attack if I do not ask his question.
Okay.
Guys, I can only get to so many questions. I'm going to try. So he wants to know, and this is a bit of an off-base one, since humans have never seen the actual structure of an atom, how do we even know what it looks like?
Because that's what they're doing in CERN in Switzerland. They accelerate the particles underground in these huge big tunnels which are kilometers in diameter, and they make them move really, really quickly, and they detect them. They don't see them with a microscope, they detect their behavior.
That's incredible. Guys, okay, we're going to take a short break. Let us know. Oh no. Oh, we are. I can't believe it. Is this the time? I cannot. Okay, guys, I've got to go. Thank you so much, grade 10s. Grade 11s, don't forget, you're on next. Grade 10s, thank you so much, and keep on the Facebook page. Thank you and goodbye.